Uh, Thank you, Joseph, for accepting our request. So Joseph is a PhD student in the Computer Science Department at Indian Institute of Technology, Hyderabad, supervised by Dr. Vineet N. Balasubramanian. He works in developing machine learning models for computer vision, which can continually learn as we humans do. His research works have been published at top venues like PPAMI, NeurIPS, CVPR, three times one oral, ECCV two times, ICHCAI, BMVC, and WACV. He received the Excellence in Research Award from IIT Hyderabad twice in 2020 and 2022 and is supported by the TCS PhD Fellowship. He was awarded with the AI Game Changers Award by NASCOM in 2022. He has been a student researcher with Google Research, visiting scholar at MBZ University of AI, UAE, and a research intern at Inception Institute of AI, UAE, and University of Tokyo, Japan. Right. So, right, Joseph has a wonderful profile, and I've went through some of his publications. He has done some great work in continual learning for object detection. And on behalf of SciTech Talks, I welcome you all for this amazing session. And over to you, Joseph, for your talk. Thank you.
Yeah, thank you very much for your generous introduction. And I believe, as I just initially mentioned, I'll be very happy if the participants in this talk actually gets away with at least some concrete bit rather than I kind of speeding over all my slides back to back. So we can keep this as much as informal as possible. So I would encourage you to kind of ask your questions or doubts anywhere down the line. So with that talk, I'll probably start sharing my screen.
And at the end, Joseph, there are a few list of questions for the participants because 38 people have registered. Probably they might be joining as your talk is going on.
Sure,
so
great.
there are a few questions from the participants who have registered. Maybe at the end, I'll list them down, and so that when your recording is going live, they can have an access to it.
Sure, of course. Yeah, I think you might have to give me access for sharing my screen.
Sorry.
Yeah.
Yeah, done.
Great. I hope you are able to see my screen.
Yes, Joseph, please go ahead.
Amazing, amazing. So, right. So before we get into the real meat of it, let me just start with a question for all of you. So, what do you think this is, or what are your initial thoughts after seeing these images?
So these are just birds. In different views. Yeah. So.
Any thoughts on what kind of birds or?
No thoughts actually. So
yeah, of course.
Any fusion takes happen in that image. It's different. The bird is looking very differently.
Oh, amazing. That's a nice thought. So this bird is looking very different from whatever you know before. Would that be correct?
Yes, sir.
Okay, great. Yeah, that's a very nice point. Anything more? Well, let me get into it. So that's nice. That was a nice comment. At the same time, let me introduce this bird to you. This is known as kakapo. This is a flightless parrot from New Zealand. And this is one of the largest parrots. So it weighs pretty heavy. So that's the reason why it cannot fly. And it shares a lot of characteristics of an owl too. It also kind of gets active at night and so on and so forth. So, so maybe when I flash you this image next, you might be able to identify the bird in here, right? I mean, this is kakapo, right? It's quite simple. And at the same time, something more interesting that is indeed happening in your head is like you are still able to identify that object that is on the left of the bird, right? So what is that? It's a human, right? So you did not indeed forget about the fact that you have something known as a human and you are able to recognize it. And at the same time, you are able to learn something new. I mean, whatever you learned new is this bird known as kakapo. Unfortunately, this is not the case for machine learning models. So in machine, assume you have a classifier, or let's say an object detector, or whatever be that, some kind of a neural network that is able to classify or detect instances that you are aware of. So that would be, let's say, all your classes that you are initially learning your classifier or object detector on. And then assume you are incrementally adding a few more set of classes to it. So once you learn the new set of classes, the classifier or the detector or the neural network get biased to the new learnings and tend to forget what it has learned before. So this problem is studied as catastrophic forgetting. And when we kind of compare it one-on-one with how we humans do learn, it's a huge mismatch, right? I mean, we are able to incrementally learn things in a very easy fashion. So all my kind of research works were along these lines, where I was trying to kind of make a neural network much more, learning of a neural network much more closer to how we humans kind of learn. So this is a big intuition. And then I'd like to maybe touch base upon two works from ours. One is on object detectors. How do you kind of incrementally learn object detectors? And we're going a step further to not just incrementally learning, but then how do you kind of identify unknown instances in the environment without labeled data for these unknowns? And at the same time, whenever we have some label, we have some annotations for these this identified unknown, can you incrementally learn that? So I'll get into it in detail, but the main takeaway from here is the way neural networks learn today is very different from how we humans tend to kind of learn and assimilate new knowledge. So let me get on to this first work, which we call as open world object detection. So this was presented at CVPR last year as an oral paper. So at a very high level, let me try to re-emphasize the problem setting that we are talking about. So this world has infinite amount of classes, right? So that is indeed captured by this gray box that you kind of have here. So at time step T1, we basically just know a few set of classes from this whole world of unlabeled, of the classes that exist in this open world, right? So these are the known instances that we kind of have. And what we are indeed tasking an object detector to kind of do is to learn how to detect these unknowns. Learn how to detect these known instances. At the same time, can you automatically identify unknown instances in your environment? So a use case would be, assume you have trained, let's say, a robot in-house, and you're trying to deploy it for some kind of a service mechanism. It's quite possible that the robot, gets into some kind of instance that is pretty novel and unknown to it from the training instances, right? So what we're trying to task a model to do here is, can you automatically identify some unknown instances? And if any of these unknown instances are indeed labeled, so these question marks indeed turn to the blue dots over here, which is the new knowns. A human or someone in the loop annotated it for you. And then in such a situation, can you kind of learn these new classes that got annotated without kind of forgetting these old set of classes that had before? So, and this is the problem setting of open world object detection. So I'll probably just pause there in case if there are any kind of clarifications that are required for that problem setting.
So do you still need the, you still assume that the annotations are there for the new incoming classes, right?
True. Yeah. So in this specific setting, we do have this part. We say that we get the annotations for the unknown sometime down the line. So in our robot example, it can be the case that the robot automatically identifies something as novel or unknown. And then maybe someone can go to it and say, okay, this is a new instance of, let's say, this class, a new specific class. In such a case, you'll get this annotated data from your environment, and can you incrementally learn those kind of instances?
Okay. So sometime back, I've went through. I was going through Tesla's AI day video. So you were just describing how they try to learn the novel classes. So right, so is this something similar to that as well? Have you listened to that Andre Karpathy's talk sometime?
I haven't listened to the specific talk that you were referring to, but I should say that class discovery per se is a pretty interesting subspace within machine learning. So a concrete instantiation of class discovery process would be, assume you have access to some label data, and then you're going to train a model. And then once you kind of deploy it in the open world, can you just identify unknown instances in your environment automatically? So in some sense, our problem statement, it is an umbrella over that, where we kind of say that, like once you kind of get some annotated data, can you kind of, incrementally learn without kind of forgetting earlier classes. But we also used to kind of have some works on class discovery, which would be presented at ECCV later this year.
Okay, that's great. Yeah, looking forward for it.
Sure, of course, yeah. Great. So this is a big picture of of open world object detection, and maybe I can give a concrete example over here just to motivate how we kind of go about doing it. So assume we have an object in this novel, open world object detector trained, and this is how you kind of do an inference. So as is quite intuitive from my explanation, we learned this incremental of open world detector in stages, right? So on your left, what you kind of see here is an open world object detector that is indeed trained to learn a set of classes, which includes person, and it hasn't been introduced to items like fruits or vegetables or household instances. So the open world detector hasn't been introduced to that. Still, or what our OWOD model, or the ORD model, which I'm going to explain in the next few slides, what it tries to do is it is able to identify person because with its semantic label, because it has been introduced to it. And at the same time, it is able to identify these unknown instances as unknown. So these labels are indeed coming from our trained open world model. And at the same time, at some time later, we are able to, so we are training this model with this extra information of of the different categories of fruits and vegetables and household instances and so on and so forth. And what we kind of see over there is the open world detector is able to incrementally learn them without indeed forgetting how to detect persons. So and interestingly, one unknown instance still remains. And because such similar instances has not been trained on, so the detector still identifies them as an unknown. So this is a big picture of open world object detection. And I just wanted to kind of throw across a qualitative example so that all of us are on the same page on what we are intending to do. So what we are doing over here is the first method. So we were introducing this problem, and at the same time proposing a baseline methodology for solving as a first step to solve this open world object detection problem. So we were building on top of our ubiquitous faster RCNN framework. So faster RCNN is a two-stage object detector. So initially, we do have a backbone network which extracts features. And from these features, we learn a region proposal network which identifies locations within this feature map which can potentially contain an object. Once this region proposal is indeed cropped to a specific size, then we kind of pass it to a classifier basically, which is inside this region of interest head. So each of the region of interest goes into this region of interest head, which also contains a few more convolution layers and ends with a classifier and a regression head. So classifier basically classifies this region proposal into one of the n classes that it is known to it. And then this regression head basically kind of gives you offsets of each of the localization bounding boxes that we kind of have. So there'll be a quick 1-minute reminder of how a faster RCNN is indeed working. So what we tend to do here is make a little bit of modifications to the faster RCNN so that it is amenable for identifying these unknown instances and the methodology for incrementally learning these identified instances. So just some ground rules over here, as this is an incremental learning setting. While you're learning something new, you don't have access to the label data of whatever you learned before. So that's number one. And the second one, important point is like, for these unknown instances, you never have labeled data saying that, this part of the image contains an instance which is unknown. So that information is also not there. So the first, first change that we kind of bring to a standard faster RCNN kind of a framework is to enforce a contrastive clustering in the latent space. So the idea and the intuition here is like, if we are able to channelize the latent space in such a way that similar instances are grouped together, and at the same time, different instances are far away from each other, it would be helpful for doing our, identifying these unknowns, right? So that's the intuition of how we kind of start off with. So first we kind of try to enforce this kind of contrastive clustering in this latent representation that you kind of have here. Concretely, what we tend to do is that for each class, we do have a class prototype PI. And for each of this class prototype, and for each of the new class each feature representation for, let's say, a new class C that we are indeed focusing on, we are trying to enforce this, a separability in the latent space, which is quite simple. Assume D is any distance metric. We are enforcing that for any specific class that which corresponds to a specific class prototype PI, if both of them are indeed matching, then the distance should be lower. If not, then it should be separated at least by a margin of delta. So this is how we kind of enforce this, contrastive clustering within the latent representation. And so each PI is also indeed learned. So this class prototype is learned on the fly, and it evolves as we kind of train. So this is how we kind of enforce a latent representational, separability in this in the basic contrastive learning framework. So interestingly, if you kind of note here, is we are saying that even the unknowns are contrastively separated from other labeled known instances, right? Which is a bit counterintuitive, because if you recall what I was saying before, we ensure that that there's no label for this, unknown instances. Now, the interesting part is, without having label to any of these unknown, let's say, region proposals, how do you kind of, identify them and make it separate in the latent space? So what we are indeed proposing is an auto-labeling methodology, which is quite simple and intuitive. So maybe I'll get to that in the next slide. So what we are indeed doing here is we are proposing a simple auto-labeling strategy, is just to sort the region proposals based on its objectness score. Once you kind of sort it, and we're gonna, so how region proposal network is indeed trained is, once you kind of have this objectness score and a region proposals that are indeed coming out from it, we measure the IOU with the ground truth. So for any of this region proposal that is not indeed matching with the ground truth, what a usual fast RCNN does is it classifies that into a background instance. Instead, what we are trying to do here is, for all the region proposals with very high objectness score, but without an overlapping ground truth, we are going to select top K of them and label them as potential unknown instances. So this is how we kind of auto-label some of the instances as unknown. And by the way, so that is just for, auto-labeling some instances over here. It is not indeed used for the final classification. So I'll get to that in a minute. So far, all we have done is enforce some kind of contrastive separation in the latent space. And for ensuring this contrastive separation, we need some kind of, pseudo labeling for even the unknowns. So for that, we are lynching on to the fact that, region proposal has high kind of, have a lot of information on, a lot of class agnostic information on what an instance can probably look like. So we are using that information for auto labeling some of the instances as unknown, and using that in the contrastive clustering formulation. So far, these are the two modifications that we have kind of done for our faster RCNN kind of a framework. And the third modification that we kind of have is to use an energy-based classification head. So just a little bit of primer about EVMs, as like EVM models has a very nice intuitive property. EBM models, whenever, so EBM is indeed trained in a bit of a contrastive fashion where you have this in-distribution data and out-of-distribution data. So the in-distribution data, the EBM is trained in such a way that energy function will indeed give you a score, an energy score, which will be minimum for the in-distribution data and max and will be higher for the out-of-distribution data. So what we kind of identified here, it kind of follows from an ICLR 2020 work from Will Gertlow. So we are kind of reusing and repurposing a standard classifier, and we are treating that as an EBM. And once you kind of treat that as an EBM, that we are able to find a very nice way to kind of identify in distribution and out of distribution data, which we are using for identifying some instances as an unknown knockdown. I mean, stepping through it a bit more in detail. So we are using this, I mean, equation number 2 is a free energy formulation from Helmholtz. So E function that you kind of see here is the energy function that we are indeed talking about. So once you have, this energy function is indeed defined per each of the label or the class that we're interested in. And the EF is how we kind of, define that energy for a specific latent vector F across all the classes. So this is how we kind of formulate the energy or kind of formulate the energy across multiple classes in a specific formulation. What we are indeed doing here is like trying to find this interesting connection between a standard, like softmax based classifier and this energy formulation. So we are going to measure, let's say, the likelihood of, let's say, a feature to belong to a specific class L, okay? And this would be a standard softmax equation, right? So where you're kind of, raising your, logits to the power x, and T is the temperature that kind of controls, like standard, softmax, nothing fancy over here. And a similar way to define a likelihood on top of this energy formulation would be what you have on the right. And both of them are measuring the same quantity, right? So we can kind of equate them. And the nice part here is here you can equate all the terms, and then but for this E factor. So this E function, you can measure the energy for this latent vector F for the specific class L. You can equate it as negative of GLF, right? So that's a specific, logit for the specific class. You can get that right from the equation, right? Once you have that, all you need to do is like just swap in, this negative G F of L over here, and then you'll get to see this equation. The nice part is this is nothing but log sum exp of your logits. That's all. So once you kind of do this, you have a very nice property which is kind of evolving. You are able to treat the classifier that you kind of have here, the standard classifier that you have here, as an energy-based classifier. Once you treat that, what we kind of do is we have a kept aside validation data where you have labeled instances for this knowns and unknowns. And then what we tend to do is like we're going to plot the energy values for this kept aside validation data. And once, so on x-axis, you have this negative energy, and then and we are just measuring the probability or given each of the sample to belong to, we're just plotting the energy for each of this kept aside data point that we kind of see. What we nicely see here is all the in distribution data, which is energy values of your known data, right? Which is in distribution data, they tend to have a higher negative energy when you see for the energy values for the unknown data. And what we do here is fit a distribution on this. What we found out is that Weibull distribution fits these kind of energy values very well. So we are fitting a distribution, and then while we are doing inference, we are measuring the likelihood for a region proposal to belong to either of this distribution to kind of auto label that as an unknown. So that is what we are indeed doing for identifying any of these instances being an unknown or not. So, I'll probably just pause there and probably take any questions. If not, I can go ahead.
So your basically the likelihood is determining your unknown, right? So that is what you're trying to say.
That's true. That's true. The likelihood. So what we tend to find here is like the likelihood for. That's a very nice way of interpreting it. Yeah, the likelihood for this label instances that you have. seen and your unlabeled instances are pretty different. And then we're kind of fitting a distribution on top of either of them, and then using that distribution, the fitted distribution, to kind of make sure whether any of the instances indeed belonging to the unknown class, or I mean, like if it belongs to the known class, then we directly go to the classification head and get the semantic label and go ahead with it.
Okay. And does this fitting happens at regular instance of time, or how does this fitting takes place?
Right. So this fitting is indeed, we are doing this fitting once we do an incremental step. So probably you get clear when I kind of explain how to kind of we go about it. I mean, our incremental setting.
Yeah, I think that's all.
Great. So that basically summarizes what we kind of do for, identifying unknown instances in this setting. So and for the, so while you kind of identify these instances, then our open world object detection indeed says that, like in future you will get these identified instances being labeled, right? And you should be incrementally learning these identified unknown instances, right? So then we will have this catastrophic forgetting problem. So in this specific work, we are just doing the very basic thing for addressing forgetting, which is very simple but works like magic, as a simple exemplar replay. We are keeping a replay buffer. We are keeping a replay buffer of n samples per task, where n is close to these 20 instances per class. And then we are replaying those instances while you're learning something new. So that's a simple exemplar replay strategy that we're kind of using over here. So, so the experimental setting that we introduced for this specific problem was in task 1, we have all the Pascal VOC classes. And in task 2, 3, and 4, we are using a disjoint set of classes from from MS COCO and grouping them semantically. So task 2 contains outdoor instances, appliances, trucks, accessories, and so on and so forth. Task 3 contains instances of sports, food, and so on and so forth. And task 4 contains kitchen items, furniture, and so on and so forth. So this is how we kind of make an experimental setting to evaluate it. So specifically, let's say we have initially we train our detector on task 1, and then if we introduce, if we show the detector any of the instances from task 2, 3, or 4, then it should be able to identify those instances as unknown, at the same time giving semantic label to the identified so for the labels of, for the instances in Pascal VOC dataset. That's the experimental setting that we kind of introduce. And so to quantitatively identify and measure how good our method is doing, we are using 2 metrics from open set literature. So wilderness impact indeed measures the a ratio of precision while you have known data and known and unknown data in your test set. So ideally, after you add your unknown data, the precision should not fall, but it falls. So ideally, if a lower value of wilderness impact would be ideal for us, close to 0. And absolute open set error basically measures the number of unknown instances that got wrongly classified into one of the known classes. And for measuring the performance of the object detector per se, we are using a standard mean average precision metric. So here is a summary of our main result. It's a bit an exhaustive table, so maybe I can step you through it. So maybe we can focus on this task 1 column. So here we do have an oracle which is trained on all your data. So here you have so this is how it is trained. It's trained on all labeled instances of Pascal VOC is the labeled set of classes that you have, and at the same time, instances from the task 2, 3, and 4 are explicitly labeled unknown for our oracle setting that we kind of have here. That is what you kind of have here. And then in faster RCNN is a standard faster RCNN, right? And our technique for addressing forgetting is fine-tuning, right? So we like balance set, exemplar set, and fine-tuning on top of that. So that is what we kind of have here as faster RCNN plus fine-tuning. And then we have our method, which we call as ORE. So that's what we kind of have. And we have a wilderness impact, absolute open set error, and the mean average precision over here. So what we tend to find out here, what we tend to see here is after learning the first task, we don't have much severe drop in performance. But when we see our absolute open set error, we have very significant improvement when we kind of for our open world, or for our OR method, right? And the same comes for the wilderness impact too. And the incremental results are not applicable as is the first task, right? So because there's nothing to forget. While you're learning task 2, we even see the same kind of response over here. Without serious drop in performance, we are able to kind of quantitatively improve our this absolute open set error and the wilderness impact. So here the nice part is the catastrophic forgetting. So in faster RCN, just learning your label data for task 2, the performance on your previously known for your task 1 instances falls catastrophically into from 54 to 4. And our simple methodology for addressing forgetting, which is this balance fine-tuning, it works like magic. It bumps it up to 51. And our method is able to kind of improve it a little bit further too. And the same indeed happens for task 3 and task 4. So this is how we kind of quantitatively evaluate it. And the nice part is an interesting observation that we kind of had was just by adding this faster RC, just by kind of quantitatively, or rather, just by explicitly modeling this unknown, we are able to improve our incremental object detection results too. So our intuition here is we're giving the model an opportunity to characterize this, confusing unknown instances into a different class. And hence, this is indeed helping it better to learn new classes better without kind of addressing, without having very severe forgetting. So, this all 20 is the upper bound, and then ILOD and faster ILOD are a couple of methods that are doing incremental object detection. And then we are, when we do our, we are able to get it a bit more better. So, so that was an interesting, byproduct of our main methodology. So these are some a bit more qualitative results on, where we are able to identify unknown instances. And then while we introduce that sometime later down the line, we are able to identify them as, give a semantic label to it. Same is the case here too. Yeah, probably I'll just pause there to take any more questions on this, or thoughts or suggestions or any discussion points at this point.
I have a quick question here, Joseph. So
Sure.
this is very, very interesting to listen to your talk, right? So this is the first step you're trying to, by using this region proposals, and the end you're trying to propose the energy-based classification laws.
Mhm.
So what I would like to know here is, so this kind of strategy can be applied very well to other two-stage detectors as well.
True.
Yeah. Right.
Yeah,
Okay.
that's true. And we had a photo of work in this CVPR where we were using it with data. So data is not two-stage, it's a bit more end-to-end with a transformer-based architecture. So it has a ConvNet as a backbone, and then from then there's a transformer-based encoder-decoder. And then we had a better way to kind of, get these unknown instances, get the pseudo label from the unknowns directly from the CNN-based backbone. And then we were doing a little bit more along the lines too. So though it was not directly adapting whatever we had into DITR, but then the main focus points that we're kind of laying down over here is, there should be some kind of methodology for identifying these unknowns automatically. And then there should be some kind of methodology to kind of add new instances and new classes to your existing detector. So these are the two kind of, sub problems within the main problem, which is indeed true for, let's say, any kind of object detector per se. Okay,
good. And I've seen from your bio some blog, right? So you were mentioning one of your experience with underwater image classification or something related to that, right? So does that problem setting also is similar to this, or that is some completely different?
Right. To be honest, it's a direct application of our open world object detection problem setting. So we do have some collaboration going on where there's a team which kind of have, let's say, robots that actually go underwater, and they examine the seafloor and the seabed for different organisms. So, I mean, the interesting part is almost majority of the living living organisms that are inside the oceans are unexplored. So what we know as let's say labeled fishes, for example, are too low. So so we are trying to kind of make a methodology where, you know, when we get this data from let's say this machine that robot that indeed goes there, captures footages, videos, or frame by frame footage that we kind of have, how are you able to identify unknown instances in this automatically? If you are able to identify the unknown instances, then our next stage also comes in, where can you have a single unified model that can identify your labeled instances that you had before and your newly identified unknown instances? Can you kind of incrementally learn that? So that's a direct application setting to our open world object detection problem.
Okay, so is there a public data set for that, or
right, right, yeah, right. So there is this data set known as PhantomNet. You can go online. So it's from Embari in the US. So PhantomNet is a large data set with this underwater footages, and then they have an amazing team. They have actually annotated most of them. So still there are a lot of the depth of the ocean are a treasure trove of infinite amount of species. So there are still many areas, and at the same time, Embari's data set, known as PhantomNet, is so good that you have tons of research questions in there. For example, underwater images are pretty different from our standard images. It's not like the guy in the tie that you see on my slide right now. Things are not very well defined, and then there are a lot of clutter, and there's this interesting problem of small object detection. Not all instances are large, so it's a treasure trove. So if anyone is indeed working along this space, I would strongly recommend to check out their data set, PhantomNet. That's amazing, and they do have some baseline models also trained on YOLO, and I believe even on RetinaNet and so on and so forth. So those are also pretty good starting points for anyone who is indeed looking into ocean-based object detection and so on and so forth.
Okay. Sure, Joseph. Thank you so much for the information. I think that's all from my side.
Okay, cool. So basically, to summarize this open world object detection, we basically had a practical extension to standard object detection problem. And it's nice to see that, we call it practical, but then we see some real life implications also for this problem setting. So that's indeed very, it's a warm feedback from a community. And then we propose a basic baseline known as OR, which basically builds on top of three components, which is contrastive clustering, unknown aware region proportion network, and this energy-based unknown identifier. And for for just setting the stage clear, we introduced an experimental setting and evaluation protocol. So I'm happy to share that this has been quite well received by the community. We have over 850 stars as of today on our official repo, and then this actually won the AI Game Changers Award from NASCOM this year. So that brings me to kind of the first part of the talk, where I wanted to kind of get you across this open world object detection. And I'll be, probably, I think I have close to 20 more minutes remaining, so it's well more time for discussing one more work. So if you have the energy, I'll probably go ahead and give you run you through another work, which is also pretty interesting.
Yeah. Please go ahead, Joseph. Thank you.
Amazing. Sure. So so far we have been in the object detection space. We were trying to incrementally learn object detectors and trying to do object detection in an open world setting. And so we're going to shift gears into a much more simpler problem, seemingly simpler problem of incremental classification. So you have a classifier, and you're going to learn these classifiers incrementally. And you're going to learn different tasks. So each task is a set of classes that you're introducing to your model. And we start off with a little bit of hypothesis. So let me run through it. So we're going to learn a model. Now, by a model, I'm going to break it down into two parts. You have a feature extractor and a classifier. Once you have this feature extractor and the classifier, you're going to learn this model on a set of on task one, let's say. So task one contains, let's say, a few set of classes. You're going to learn it. And then we are assuming that the latent representation, the latent space that you can have here, Z's, right? So I'm plotting the Z's over here. And these Z's, it can be well aligned in the latent representation because you have label data, you're going to train it, you train your model for, let's say, train your model well with for a few set of epochs, right? So you're going to do well. So once you kind of do that, and you're introducing your task 2 to the model. Now here you are adding a new set of classes to your model. So you're expanding your model head from your F201 to F22, okay? And then you're expanding the model, you're adding a new set of classes, and now you have access to only your new set of classes. So with your new set of classes, while you're kind of learning, we are kind of plotting the latent representation of your new classes, let it be anywhere in the latent space. But something that we are interested in here is the feature extractor that you kind of have here can get biased. And due to this bias, this latent representation that you have for your earlier class data points that can probably shift, right? So and this shift might be the reason for the catastrophic forgetting. That's the hypothesis that we kind of start off with. And we have a methodology. We have a methodology to kind of undo this representational shift. How we kind of, is there a way to kind of, as those green arrows are indeed showing, is there some way that we can kind of route back the shifted latents to where it were in this, latent space? So that's the, I'll get into how we're kind of going it, but that's a big intuition that we're kind of laying down over here. So while we are learning incrementally, we are hypothesizing that there will be latent representation shift. And then, can we propose a methodology to undo this representation shift? That is what we are indeed kind of doing over here. So any questions on that high level picture that I wanted to convey?
I think that's fine. Yeah.
Great. Now let's get into details on how we can maybe identify and do this. Undo this representational shift. So concretely, I'm going to define an energy-based model over here. So energy-based model is nothing but characterized by an energy function. So energy function it can be any function that indeed takes a vector representation as an input and gives you back a scalar. So this scalar is known as an energy value. So this function is also known as value function for instance. So once you define this energy function, we can define an energy-based model as nothing but a Gibbs distribution of this energy function, right? So, and the likelihood for this energy function can be written like this. Is nothing but standard log likelihood, and the gradient for this likelihood can be expanded like this. So this is nice, and it has two components, which is very well nicely suited. So let me walk you through it. So for any data that is indeed sampled from the real distribution, we're going to learn the model in such a way that it will have lower energy value. And for any value, any data that is indeed coming from an out of distribution, then such data points should have much higher energy value. So this is the gradient of this log likelihood. And now if you kind of pay attention, here you kind of sampling from this energy function, energy model, right, which is intractable. So to tractably get an estimate for sampling from this distribution, we lynch onto a Langevin sampling mechanism to kind of iteratively sample from this distribution. With that, high level intuition on what exactly is an energy-based model, let me get on to how we are kind of using this, repurposing this into our specific problem setting. So whatever I just explained that the previous slide is a primer on standard energy-based model. Now, a couple of things to kind of, make our problem setting closer to theirs is to define what is in distribution data. what is the outer distribution data? Just defining that helps us to kind of transpose us and make use of the energy-based ABM model in a positive way. Down the slide. So this is what we kind of do. While we are learning a new task, we are assuming that we have access to your previous task, feature extractor trained until your previous task. And then you have the feature extractor trained including your current task. And then we are assuming that we have access to your current task data points. Now, we are going to get the latent representations of these images, pass through your model trained until your previous task, and then these latent representations, we are taking that as an in-distribution data. And for these latent representations, we are going to have much lower energy in our energy manifold. We're going to train our EBM in such a way that these latents will have lower energy in the manifold. And the same set of data, when you kind of pass through the model that is trained until including the newer task, we're going to learn the EBM in such a way that it will have a higher, and it will occupy the higher energy band in the manifold. This is how we're kind of learning the energy manifold. Once you kind of learn that manifold, we can use this to undo the representational shift. So, the algorithm that you have on the left basically steps through what I just explained. Let me take you through it. So essentially, we have three items as our input. We have a feature extractor that is trained until the current task, feature extractor trained until the previous task, and then you have the current task data. That's all you did. That's all you have, right? So first, we're going to sample some data from your current task, get the latent representation by passing this input through your previous task and your current task. Feature extractor trained until your previous task and the feature extractor trained until your current task. Once you kind of do that, we're going to sample from the EPM. Basically, we are going to we're going to do this part of the equation number 8 over here. We're going to first sample from the EPM, which with Z to T as its starting point. And then we're going to define the in-distribution energy as the energy of the latent representations that are indeed passed through your trained until the previous task. We're going to call it as in-distribution energy. And these sample latent representations, we're going to get its energy value and then call it as outer distribution energy. I refer to that as outer distribution energy. Likelihood is nothing but in-distribution energy plus outer distribution energy, negative of in-distribution energy plus outer distribution. That is nothing but this equation 8 that you kind of have here. That's all that we do, and we optimize ABM to kind of maximize this. Once you kind of learn the EBM, this very nice part to the story here is that once we are assuming that there will be shifts in this latent representation, right? So once this shifted, when a latent representation it shifts from where it were, it's quite certain. Certainly, we can probably say that it occupies a higher energy area in your manifold, right? Because it has shifted from where it were. Then using this energy-based model, we are able to find a way to traverse this energy manifold to a lower energy part of the manifold. Accordingly, go and update your latent representation Z2. So, it's pretty simple. You take the gradient of this, the latent representation that you indeed have with respect to the energy model that you kind of have, and you update your latent representation in the negative direction of your gradient with respect to this energy-based model. That's all that you do. And the beautiful part is LI, which is energy-based latent aligner for incremental learning, identifies what part of the latent. So latent is basically a vector of let's say n dimension, right? So each of this dimension can be changed. So LI actually finds out what to change, how much to change. So these two interesting characteristics are automatically captured by how we kind of learn and use this EBM. So maybe so far I've kind of used a little bit of a hypothesis that there are shifts in the latent representation while you're learning something new. And once you are learning, and once you have kind of learned, you can undo this representation shift and so on and so forth. So to concretely get that through, I kind of conducted a simple toy experiment. So this is MNIST, standard MNIST, and then I'm going to define a class incremental version of MNIST. So the first task basically contains a few set of classes, which is 0, 1, 2, 3, and 4. The first 4 classes are feminist. Sorry, first 5 classes are feminist. And then task 2 is learning the same model on the last 5 classes of feminist. And what we do here is we're going to learn a standard classifier. So we are going to use an MLP. So it's a single hidden layer MLP that we're going to use here. First, we're going to learn this model on task 1. And then we're going to evaluate the model on task 1. So here, just pay attention to the blue bars that you kind of see over here. So the blue bar over here is you're learning on task 1, you're evaluating on task 1. You see an amazing 99.19 accuracy. Then you're going to learn the same model on task 2. And then you're going to measure its performance on task 1. Now, there's a huge drop from 99 to 20%. Then you're going to use our LI to kind of undo this representational shift. Just by doing that, we are able to bump it up all the way from 20 to 83. So this basically gives us a hypothesis that there's something good to the LI-based methodology that we're kind of proposing, where we're kind of undo this representational shift. So we conducted the same experiment with latent dimension of 512 too. So if you recall, we had a single layer, hidden layer neural network, right? So the blue bars that you can see here is when the hidden layer contains 32 neurons, we're going to expand it to 512. We're going to repeat the experiment, same experiment again. So here also there is fall in accuracy close to 10%. Fall is not huge because there's a higher capacity model that you kind of have here, but still LI is able to realign them all the way into 99. Something that's more beautiful over here is to visualize a latent space. So what you kind of see over here is the latent space of your task 1 latents after learning task 1. So it's quite well separated, and it links to this 99.54 accuracy that you can kind of have here. Then after learning task 2, I mean, we can see some kind of clutter in the latent space, right? So these oranges are kind of intermingled over here. The space between, these oranges and this dark red are kind of, much more, there's much more overlap over here. Same case here, and so on and so forth. Interestingly, we're gonna use LI, and we can see this, nice kind of, pathway which the orange dots are taking over here into where it were. So it's pretty nice to kind of, see this result where we are able to identify how much of what part of the latent to shift, and shifting that is able to kind of revert back the representational shift that happened in the latent space. Something even more interesting is to kind of visualize how much of what this latent representation is indeed changing. So going back to this experiment, so this blue bars, we had a latent dimension of 32, right? So in this setup, what we are trying in this plot, what we are trying to see here is this is a 32-dimensional latent representation that you kind of have. And for each of the Langevin steps, we are doing 30 Langevin iteration. For each of the Langevin steps, we are measuring the difference. We are measuring the difference from your first, where you initially start off, right? So what you have as a column in 30 is basically you have an adapted latent, minus where you initially started off, right? So what you can see here is there's a nice progression of some kind of the latents are automatically able to identify that the EVM is automatically able to identify that this 11th latent, it should be shifted by +8, and then let's say this 12th latent, and the 11th latent should be adapted by -24, and let's say this the 5th latent and 6th latent don't touch it much, let's not adapt it, and maybe. So the takeaway here is the model, the EVM is able to identify what part of which latent to be adapted automatically. We are not explicitly enforcing anything while we are learning. So this brings me to kind of sharing how exactly EVM is and some intuitions on why we think this is actually indeed working. And I was just walking you through our detailed analysis on our proposed method. And to quantitatively measure how good we are indeed doing, we are gonna. One nice point which I forgot to mention so far is if you understand, LI is a plug and play mechanism. We are not doing anything in the training per se. We always work on top of trained models. So this allows us to kind of sit on top of incremental learning methods. So you have an incremental learning method, which incrementally learns new tasks. Let it go ahead and complete its learning. Then you end up with a model. Give us a model. We'll play around with the latent representation. We will undo the representation shift inside the model. And then, it can get you kind of, improve your incremental learning. So that's the kind of, point that we kind of bring to the community. So we have added this to incremental classifiers and incremental object detectors. So in classifiers, we actually went on to kind of experiment on 2 different settings. So in standard incremental learning paradigm in the community, there are 2 ways that we kind of evaluate it. So the first way is train a model. On the first task, you're going to train the model on the first 50% of your classes. For instances, in CVPR 100, you're going to train the first model on 50 classes, and then incrementally add the next 50 classes and in different tasks. We're going to do that. And at the same time, we're going to have experiments where we are having equal number of classes per task. So going back to CVPR 100, and let's say we're going to take a 10 task setting. Each of the 10 tasks will have 10 classes, 10 new classes being added on. And we have an experimental setting on object detection on Pascal VOC2. I'll step through those details next. So yeah, so this table basically summarizes our result, where this is, this subpart of the table is when you're training your model on the first 50 classes in your first task. And then here is where you have equal number of classes per task. And this is on CVPR 100 and ImageNet. We experiment on 5 tasks, 10 tasks, 25 task setting across the board. So we take ICARD, which is a standard incremental learning methodology that we kind of have. And once we have ICARD, we add LI to it. Excuse me. Yeah. Yeah, sure. And then we add LI to it, and we see a quite significant improvement in performance, a 6% improvement while you add LI. And then we have it across the board now on all the data sets. We add LI to Loser, which actually came out 2 years later in CVPR, and across the board, we are able to improve its accuracy too. And also in ANET, which came out in last year CVPR. So this is how we kind of quantitatively evaluate our proposed aligner. And then we do it for ImageNet 1000, the large ImageNet 1000 data set too. So here all the dotted lines are our methods without using LI, and the strong lines are using our LI. So across the board, we are able to see a very good improvement. And this is where we kind of add LI to incremental object detectors. So IOD is an incremental object detector. So it's also our work which got accepted at PAMI, where we had a meta-learning based methodology for doing incremental object detection. So we added LI to IOD, and then we were able to see very significant improvement in performance. So the baselines are, these two, we did see that in our when we discuss OR, and then we are comparing against OR also, and then IOD, we're just adding LI on top of that, and then so yeah, maybe I should explain a bit more. Maybe I did not do that in my previous talk. Is like these are 2-stage setting. So you have 10 classes first, and then you're gonna incrementally learn the next 10 classes. So it's a 10 plus 10 setting. And these classes are from the Pascal VOC. Then we are going to experiment the same with the 15 plus 5 setting and a 19 plus 1 setting. So across the board, we are able to see a quite strong improvement when we add LI to an incremental object detector too. So right, so that pretty much brings me to whatever I wanted to share about LI, where we are able to identify how much of which latent to automatically realign so that we can address food kitting. And the nice part is like we are just plug and play into incremental detectors and classifiers. Right. So with that, I think I can open the floor for the questions, and then yeah.
Participants, any specific questions before? I have a few anyways, but yeah, I would request participants to come forward if they have any specific questions.
So here the hypothesis made is for untrained model, you have assigned the lower energy level, and the trained model assigned the higher energy level, right?
Yeah, thank you for
The
the
energy
question.
manifold.
Yeah. Thank you for your question. You did catch that almost clearly, but then there's one important difference. There's no untrained model per se here.
Yeah,
At any point, we'll have, let's say here we have a model trained under the first task. And then while you're learning the second task, you're gonna use the model that is trained, on a first task over here. So this T-1 will refer to as T1, and this will be T2 in our specific example. So, so in this incremental setting, assume you are learning your nth task or your teeth task to align myself to this notation that I have used. While you're learning your teeth task, the latents of your model that is trained until T-1th task will have lower energy in your manifold, and your model that is trained on your current task will have a higher energy in your manifold.
Okay.
Thanks for the question, Edwin. Yeah.
Thank you.
So Joseph, this right. So I just wanted to ask. So so the first one, the energy-based classifier loss, whatever you're talking, right? So you if I understand correctly, there also you're using a similar hypothesis, right?
Okay.
So what is the distinction between these two works primarily here?
Yeah, thanks for the nice question. So in a first or setting that we can have used, we never trained an ABM. We never had a loss term for the energy. So maybe I think that's something that I need to explain a bit more further here. So here we were using a standard classifier trained on softmax and repurposing that as an EBM. So we are kind of treating an EBM treating a standard classifier as an EBM. And then once you treat it so, we are utilizing the properties of an EBM to analyze it further. So once you have this EBM, once you kind of look at a classifier as an EBM, which was introduced in this ICLEAR paper, your classifier is secretly an energy-based model, and you should treat it like one. So once you kind of treat the classifier as an EBM, then we kind of analyze the energy that classifier is indeed giving for in distribution or out of distribution. So that from then on, the rest follows. So the in distribution data has lower energy, and then out distribution has higher energy. So we fit the distribution on top of that, and then sample based on likelihood. And that's what we did here. And in our LI, what we tend to do is that we are explicitly learning an EBM. We're going to learn that EBM in such a way that lower energy, lower part of the manifold corresponds to your previous task, higher part of the manifold corresponds to your new task. And then once you do that, we know how to kind of adapt your latent representations back.
But still in this adaptation process, you're trying to refine your trained model, right? Still.
No. What we are indeed doing here is, that's also a nice question. So it's like you have this trained model.
Yeah.
That as of now, this model is trained until your new task, right? Now we are selectively modifying the latent representations of the latents of your previous task. And then adapting it. So while you're doing this, we're not modifying the model per se. And that's how we are indeed a plug and play mechanism. We don't kind of mess up with, if you go to our results, we add LI to ICAL, loser, and ANN. So these are all huge methods in incremental learning. ICAL, there's something like exemplary play plus a distillation-based loss formulation. Loser steps up even further, adding a few more techniques for doing a better distillation using L1 norm and so on and so forth. ANN adaptively grows your. It has a two-phased. two-channel network, and then they have a method to kind of combine these multi-channels into for learning continually and so on and so forth. So these are all huge methods. And then the nice part is, I mean, we just sit in between. I mean, we don't get into the training process at all. Once you train it, give the model to us. We will analyze the latent, and we will identify how much of what to adapt. We'll just go ahead and do it.
Okay. So you're just extracting the latents, and then you're trying to modify those latents accordingly based on your requirement.
That's true. That's true.
Okay. So you're not fine-tuning the backbone feature extractor at all during this process.
No. Yeah. I mean, I should say that would be an interesting follow-up work to take it up, where can you maybe analyze this? I mean, make use of the data or information in your EBM on characterizing in distribution and out of distribution even further. Can you take it further into your training process altogether? But once you do that, something that you might lose is this plug and play capability, because we should be we are interfering in the training process altogether too. Yeah, but I would say that is a very interesting research direction going forward.
Okay. Yeah, good. And okay, so here mainly you are working on the classification part of the work, right? So in the incremental, but the detection means it's like you have an additional bounding box regression term also. Right. So don't you think that we need to work on the bounding box regression part as well to adapt to the new, say, if the incoming objects have a different kind of an aspect ratio of bounding boxes, don't you think it needs to be adapted as well? Or is it getting done implicitly in some form in your work?
Nice. Yeah, thanks again. So that's a question specific to, let's say, incremental object detection or open world object detection problem setting. And over there, the nice part here is maybe I can use a specific point that you brought about regarding aspect ratio. Now, these different images of different aspect ratios, these can indeed come for the labeled instances too. And at the same time, it's just about the classes that we're bothered about, right? So in some sense, the bounding box offsets are class agnostic, because there's no kind of leakage of class specificity that is indeed going to that branch. So the harder part is to kind of identify and improve your classification head of an object detector, because that's class specific. You're going to add something new. So I didn't have it on the slides, but then we had some experiments where what will indeed happen when you kind of just use an object detector on a standard object detector that is trained on, let's say, n classes. When you're going to forward pass some instances that are outside these n classes that you kind of see, and what will indeed happen. So there's a nice paper from Akshay from University of Colorado in WACWI 2021, where the paper is titled "The Elephant of Object Detection: The Open Set Problem." So what indeed a standard object detector does is that it will confidently predict unknown instances into one of the known classes. Now, I brought up this point just because there is trouble in the classifier, but the localization component is quite very confident on localizing these unknown instances.
Okay. Thanks, Joseph. So I think I have. Sorry. Yeah. So this is much from your work, Joseph. So, and there are a few other questions which I wanted to ask, right? So, if somebody wants to get started with this EBMs, learning about EBMs, right? So this is with respect to, because this talk was more targeted towards the researchers who are getting started in this field.
Sure.
So I was wanted to know what was your basic motivation or how for choosing this specific problem, or did you had an inspiration from at some point? Okay, so this is the point. Okay, this is what was very much interesting. Or what was your main motivation to choose this research problem, and how to get started with EBMs? If you can throw some light on that, that would be very useful.
Sure. Yeah, I think I can decompose the problem and like the question into two parts. One is, one is a specific question on, how to get started in ABM, and the other I think is a much more generic question, and I think that question doesn't really link to the EBM part, right? So I think these are two different parts, right?
Yeah.
So in that case, getting started to EBM, I think Jan LeCun is the guy who is kind of pushing for EBM. So so EBMs are just, like he has amazing tutorials, even tutorials on EBM, and there's one paper which is titled, I think, Tutorials on EBM from LeCun. So to get started in EBM, I think that would be a nice place, and at the same time, it would be nice to kind of go through. There's a specific part of even in my paper where we're kind of explaining the basics of EBM and linking to papers in this specific area. So I think if someone is interested, I think they can probably go ahead and check it out. And the second one, how do you, like, would the question be something like, how do you kind of, why did you kind of choose working on continual learning per se, or?
Yes. What was your motivation basically?
Right. So my motivation was, basically I had this thing inside my head where we humans are super cool in doing many things. So are there some specific areas where which there's a huge difference in the way that we operate and the machine learning models operate? So I had this intuition in my head. I was a master's student also at IIT Hyderabad. So during those days, I used to work a lot on object detections, and one of our work was presented at a workshop at ECCV back in 2018. So at that point, I got a chance to kind of go and meet with a lot of pioneers in this continual learning space, and that in 2018, continual learning was just picking up. And then there was this exact match of what intuitions that I had in my mind on finding a problem that is very different with how we do and the machine learning model do. And this, I was pretty captivated by the problem setting. So the authors of ICAL and like there's a couple of other people. There's a professor by name Christopher Lampert from IST Austria. He is he's a guy who came up with ICAR. There's another professor from KU Leuven Utrecht. So all these people were organizing a workshop on continual learning and related areas. So attending that was pretty interesting and important for me because many of the topics that were discussed was very close to my heart. So I picked it up from there. I discussed with my supervisor, and we agreed upon the fact that there's something interesting that we work on. So it's been a fantastic ride since then, and we have been able to make contributions to the community in this incremental classifiers, and then our first work was on was on a meta consolidation idea, which was presented at NeurIPS in 2020. And then later on, I had some expertise in object detection too. So it was obvious to mix and match. When these two, incremental object detection was a pretty obvious problem statement for me. So because it's super interesting to do, right? So that also worked out positively as at PAMI. And then while we was kind of working on incremental object detection, something that's pretty intuitive. Again, going back to my analogy of humans and machines is, whenever we see some instance that we really don't know, in the earlier part of the talk, Vijay Lakshmi did indeed find out, and she did indeed say that those images that I saw is different from whatever I know. So that's an instinct that we all possess. So can we make a machine learning model do that? So that's the question that I started off asking, and then that's how characterize the problem of unknown identification, and then incrementally learning this identified unknown. That's how open world object detection came around. And then so while I used to work on open world object detection, it's like we were focused on this unknown identification. So so I think you had a question earlier in the talk that how do you kind of analyze and characterize these unknowns per se? So so that specific problem setting, I isolated that from object detection back to classification. worked on that, and that's indeed we have a contribution on novel class discovery coming up in this ECCV. So I mean, fundamentally, it's all about chasing your intuitions and holding tight to it, and then the rest just came along.
Thank you so much, Joseph, for sharing this knowledge. And I see that you have the relationship with the external universities apart from IIT Hyderabad. So, how did you find such kind of an internships or finding such collaborations? So, what was that starting point, which or where did it start? Right. So, if somebody wants to get started in a collaborative work,
Sure.
Even with your team, say, what will be the good starting point for them?
Yeah, I mean, the simple and the most important thing is reach out. I mean, that's important.
Okay.
So no one will, unless until you reach out, I mean, it's not, and it's, that's the first thing that we should do. And personally for me, like after I submitted something to CVPR back in 2020, which got rejected and eventually got accepted at NeurIPS the next year. So at that point, I mean, it was 2019, sorry. I had applied to MBZU AI. Inception Institute of AI in Abu Dhabi. So I'm not sure how many of you might be familiar with it. It's a research organization in the Abu Dhabi, pretty very well heavily invested in vision related tasks. And then, I mean, to concretely answer your question, how did I kind of reach out to them? Is just because I read one of their papers, which is very well aligned to class incremental learning setting. So at that CVPR, Jatushan, who is one of my co-authors and in my PAMI paper, he had a paper, and then they were actively working on incremental learning. So I mean, for them, I mean, I also used to work on incremental learning. For me, they used to work on the same thing. So it was a perfect alignment of an interest. And there's amazing people over there. Salman Khan, Farhad Khan. So I mean, like getting to know them was very good for me. So we started collaborating. I did a 6 months internship there. I returned back to India. I kind of remotely work with them for the next CVPR. That's how we kind of pulled off open world object detection. And then after that, I mean, like I had applied for an internship with Google. So they also came out positively. So at Google, I was in Google Research India. So even there's a good team which does computer vision research. So I just pitched the problem of of our class discovery to them. So at Google there was another person who was also a affiliate member at Google. So he's a professor at University of Hong Kong. So he's a guy for NCD. So I just reached out to him. So he was also interested in whatever we are doing. So finally, we have a paper at ACCV this year, and then we had another paper at a workshop in CVPR where we won the best paper on triple mention. So this is how all the collaborations worked out. So I didn't chase out for collaborations. Everything just organically, I mean, came along.
Okay, that's very nice to hear, Joseph. I think that's good if something turns out positively when you just reply to a collaborator and then they respond to you positively. That's the most happiest thing that a researcher can look out for.
Right. And I believe, I mean, networking with people is also important. So I had a chance to attend CVPR this year. So I mean, going there, meeting a lot of people, and then I mean, it so happens that your next collaborator is just next to you. You just start talking, and then so I do have some new collaborations indeed coming up, just because of the CVPR visit. And at the same time, there are a lot of people who are interested in our problem setting. So we do get requests, I mean, reaching out to us also.
Okay. Okay.
So, yeah.
Sure. Yeah. I think I'm done with my questions. Before I thank the speaker, does participants have any more questions? If they have, please unmute yourself and ask Joseph. Good. I think I assume that there are no more questions, Joseph. And thank you so much for your time today. I think it was a great learning for me as well. Right. So I have a great association with your lab indirectly. Right. So starting from Mr. Argyapal, Dr. Argyapal, who is now a postdoc in Harvard, right? If I remember correctly, last year.
Yeah, he got a tenure track position at I forgot university in Australia. So
Okay, that's good to hear.
he's now a professor at Monash in Australia. Yeah.
Okay, yeah. I have a great association. Although I never interacted with Professor Vinny, right? So at least now, because of you, it's like it was a different learning from Agya that I had when he was interning at TCS Research, and now it's a different kind of learning through this webinar that I had through you. I
Sure.
think I have a lot of ideas in my mind, and Mr. Alabaksh, in fact, is venturing into getting started his research in this field. Probably, if needed, we will definitely connect to you back and then talk to you in case if there are any specific queries for him
Sure.
going forward. Yeah.
Of course.
Yeah, thank you so much, Joseph, for your time. Thank you so much for
Most
your valuable
welcome.
time, and looking forward. All the best for your thesis for your defense, which is coming up.
Sure. Thank you so much, and thank you so much for having me and having this opportunity. Thank you so much.
Yeah, thanks, Joseph.
Thank
Bye.
you, sir. We got many more inputs from you as a starting. We are going to start the research, and your inputs regarding the internship, and also your clear idea. You have segmented your full work clearly, and you have bounded clear works. So this input helps me a lot. I got many more inputs from your valuable points.
I'm really happy that when this, let's say, an hour and a half was valuable for you, and I'm very happy for that. Thank you.
Yeah, thank you, sir.
Yeah. Thank you, Joseph. We'll get back to you soon in case if needed. Yeah.
Of course. Yeah. Sure.
Yeah. Sure. Thank you. Bye.
Thank you then. Bye.